Hey everybody. Today we're doing an example of hypothesis testing in the situation where the population standard deviation sigma isn't known and we have to use the sample standard deviation s instead. That is, we're going to do a hypothesis test using the t-distribution. Here's the example we're going to work through. I recommend pausing the video, trying this on your own before watching my solution. The mean carbon uptake rate in a certain species of grass is thought to be 34.0 micromoles per square meter per second. Questioning this, a group of researchers looks at a random sample of 42 patches of grass, finding a mean rate of 30.6 with a standard deviation of 9.7. Working at significance level alpha equals 0.05, is there sufficient evidence to doubt the conventional wisdom about this species? So this is going to use the t-distribution because we only know a sample standard deviation, not a population standard deviation. We are going to want to do several steps in our process here. First, we're going to want to carefully state null and alternative hypotheses, then compute a test statistic, in this case t, then compute a p-value using that. After that, we need to properly interpret the p-value to make a decision about whether or not to reject the null hypothesis. And finally, we're going to want to give a conclusion in ordinary human language. So let's get to it. Here are my hypotheses. I'm going to use the null hypothesis that the population mean is 34.0 and an alternative hypothesis that it's not 34.0. A couple comments about these. First of all, notice that my hypotheses, both of them, are just referring to parameters, to information about the population. And this should always be the case. You should never have any sort of sample data in your hypotheses or even informing your hypotheses. Best practice in the real world is to set your hypotheses before the data is actually even collected. Secondly, notice that I've used a two-sided alternative hypothesis. That should be sort of your default unless you have a very specific reason to only be concerned with the possibility that a parameter is less than the null hypothesis value or that it's greater than the null hypothesis value. Next, we compute a test statistic for our sample. And since we only know the sample standard deviation s, not the population standard deviation sigma, this is going to be a t-statistic. The formula for it is x bar minus mu naught divided by s over root n, where x bar is our sample mean, mu naught is the population mean under the null hypothesis, so basically the null hypothesis value, s is the sample standard deviation, and n is the sample size. So those are all things we can plug in. The sample mean was 30.6, the population mean under the null hypothesis was 34.0, etc. When we plug in and we do the arithmetic there, we get t is negative 2.27. So that number is supposed to be quantifying how far away the sample mean that we got, 30.6, is from what we expected, 34.0, under the null hypothesis. We're going to use that test statistic to compute a p-value, and we're going to do that using the distribution t of 41, t of n minus 1, where n is 42. Here's the picture. I have labeled the test statistic that we've got, negative 2.27, in the distribution t of 41. We need to find the probability of getting a test statistic at random that's more extreme than the one we actually got. So I'm shading the area to the left of negative 2.27 and then also shading the area to the right of positive 2.27. Of course, both those areas are the same. So I'm going to get one of the areas, the probability that t is less than negative 2.27 just by random chance, and then I will double that. You should do that using technology. I use R, where the command that I need is 2 times pt of negative 2.27, comma 41. The output is 0.028. So if the null hypothesis is true, data like what we got or more extreme than what we got will happen about 2.8% of the time. Since the p-value of 0.028 is less than the significance level alpha, 0.05, we reject the null hypothesis. There's good evidence to conclude that the mean carbon dioxide uptake rate in this species of grass is not actually 34.0 micromoles per meter squared per second.